Okay, so thank you everyone for turning up to this week's webinar. So this week we're going to be going over setting up a front-end crash analysis of an FSA vehicle. The model that I've been given is just a generic model from RMIT's FSAE, so big thank you to them for allowing me to use this. So I guess a quick background on nonlinear structures in particularly on this one, is what we're really going to be looking for today is about the absorption of energy from kinetic to internal, or the change of energy, I should say, because energy is merely just transferred. And we're going to be looking at how it transfers from kinetic energy to internal energy. So one thing to remember is with this setup, if there is actual FSA rules and regulations as to how they would like you to set up a front structure that you've designed yourself, then definitely do the same setup as you would in regards to that. But for this setup, I've just got some generic understanding that it would be 350 kilograms traveling at 7 meters per second. So that is how this will be set up today. And we'll be going through some basic stuff that we already have covered recently, just to give a bit quick background, such as on 2D meshing, mid-surfacing, and also the rigids, the rigid elements. So this week we'll be using RBE2s. Last week we used both RBE2s and RBE3s. So just a little bit of background on that. So hopefully everyone can see the model that we've got up here. And I've already split out my components just to make it a bit quicker into the crush structure, the moving rigid, and then for this, you always need to make sure that you've got separate components for each separate rigid element. Not too sure why, it's just how, I guess, Radios is running through Hypermesh. But it does help in a way, though, because it really helps to distinguish what components are associated to which elements. And also for the profile, making sure that we're always in the correct profile when this wants to open up. Okay, so it doesn't want to open up, that's okay, but making sure that you're in the Radios profile. Hang on. Whoop. Should be sharing. Sorry, it was just loaded. No one could see my screen. Sorry about that. Everyone should be able to see it now, though. So I'll just quickly go back. Just make sure you can see my screen. Yep, beautiful. So it's okay. So just on that, making sure that the profile that you're starting up in is a Radios profile. And with all your components in the tree here, you can see that I've got it split out in the crush structure, moving rigid, and then I'm going to have two rigid body elements, and each one of them will be in separate components. So the reason why you split these out is because in Radios, you can either, when you click, hang on, sorry, I'm just going to have to reload this because it's, I'm just going to pause the recording and reload it. Okay, so now it's working again. Making sure we're in the Radios section. So in the user profile, always select your Radios. And I'll show, actually, I'll just reload up the model, but for this one, we're going to import a solver deck and making sure the file type, so when you're importing the solver deck, making sure the file type is selected to Radios, and then we'll just open up the run. Oh wait, sorry, go model. So I'm going to import the model that I had. So yeah, you can do either, just like in OptiStruct. So it's always handy just to try each one as you would like to. Okay, so as I was saying, back with the rigid bodies. Reason why we split them out into the components And this is a good way up the top here as well. It says radius, block, and radius. So that's a good way to know what profile you're in as well. So back to the components and how we can know that is each component you have to give a property ID and a material, but also you need to give a card image, and you tell it that it is a part. So every part in the model, you'll tell the solver that it's a part. So this is then, once this happens, you are then able to tell it, give it either a property and a material, or tell it that it's a rigid body. So this distinguishes between the two, and that's why they all have to be split out like this. So each structure is split out, and each rigid body element is split out. And for the rigid bodies, we're going to tell them that they're just a rigid body, and that's where our rigid body elements are going to be placed. So as you can see, these ones are already up, and how I've done that has been discussed last week, but I'll just quickly go back through the creating of this, just in case anyone missed it. It's just in Mesh, create 1D element, and for this it's called rigids. And then I would change it to multiple nodes, and then calculate node, and then select all the nodes I want to join it to. And that's how the rigids are created. And then you make sure that they're placed in the correct component as well. So for this as well, for the rigid body on the back of the crush structure, how that is connected is only on this side plate here. So as you can see, there's an edge flange when the screen comes up. There's an edge flange here around the edge of it, and you can see the line there because on their structure this is actually enclosed in. So I've only rigidized the very edge of it, but again, when doing this, making sure that you set it up correctly for your vehicle and correctly if it is properly specified in the FSA rules is a big point as to where these rigids would be set up. So making sure that you do specify exactly where, and making sure you know exactly where they're meant to be is a really big thing. Otherwise, your results can be completely wrong if that's not. So I just want to make that clear that this is how this case is set up, but definitely for everyone else, it could be slightly different. So turn out of there. Now with the elements as well, there's one thing that we didn't show last time was about the time step. So the time step is a really big thing for radios because each element has every element will have a time step, and that is dependent on the speed of sound through the element. So basically, the smaller the element, the smaller the time step, and the longer the analysis will take. So how we check this is we go into Tools or Tool, check elements, making sure that we're down the side here where we're normally working in the 2D section. You want to click on the time, and then you click check elements. So then you can select your elements, but this is where, I'm not sure why it's telling me I've got notice no valid elements, but this is where then the time step comes into it, and you can put in the same thing like a failure criteria, and when you check them, it also shows all the minimum values as well. So normally for this, you probably want to be having up around e to the -6, e -7. I wouldn't go much lower than e -7 unless it's absolutely necessary, or else you can really start increasing the time of a nonlinear run like this. So really be careful with that. Normally I'd have a failure criteria of around e to the -6 and e to the -7. So yeah, always be mindful of that. So always do tool, check elements, time, making sure that you check the time step in each element, and it will tell you the minimum time as well. Okay, so into setting up the nonlinear model. I've already set up some load collectors here, such as velocity, mass constraint, and a backing plate constraint. So with this, because we are going to be modeling this plate here, the rigid body number 7, moving at 7 meters per second, what we can do is we can apply an initial velocity to it. So how we do that is by creating your load collector. Again, this has gone through previously, so if you have missed some of this stuff, definitely recommend going back and watching the other tutorials. And in the card image section, you click initial ini-vel or initial velocity collector, and you're able to then just give it a velocity. And this one's going to be in meters per second, so making sure that your units are consistent. And I've got mine going in the negative Z axis. So as you can see, it conforms to the global axis down in this bottom left corner here. And it's moving negative along the Z axis at 7 meters per second. So that there is now the velocity collector, and that is applied to this whole plate. So, and then again, you've got mass constraint. Constraint. So we want to constrain my moving collector, because I only want it to move in the Z direction. I don't want it to move with any other rotations or any other translations. So it can only move in one direction. And then also I have created a back plate constraint, which will mean this section here will hold. And I have done that as it would be on the car. So it would be there'd be no translation and no rotation. But again, setting up this constraint is definitely want to do it to how your car model is. But I think if you're doing the front, you should be fine with doing all translations and rotations as fixed, because that way then that would be modeling it connected directly to your car. But if there is different guidelines as to how to set it out like that. Now, what we need to do is we need to attach these sections to nodes. So you'll see here a node group to which the boundary conditions are applied. So this is what we need to do now. We need to do what's called create a set. So you'll see another section down here called sets 9. What we're going to do is we're going to create 3 sets. One for our velocity, one for our mass constraint, one for our backplate constraint. So for that, right click, create set, and then we're just going to go velocity, create set, backplate, create set, and then this will be velocity constraint. Okay, so now what we want to do is as well, we want to change the card image. So by clicking on that, because we want to turn it to GR node. So that way then we can get it in the same condition as the collector asks for down here. GR node, and then our sets are going to be nodes, not elements. So so for the velocity constraint, we only need to pick one node, and to make sure we pick the correct node, what we'll do is we'll hide all the other elements and geometry, but we don't need to. So that way then we're going to go GR node, non-ordered, entity IDs, nodes, and then just select that middle node. And that's now created the set. And you want to do that to the rest of them. Change that shell card image to a GR node, yes. And we only need to select the middle node. So we're going to zoom in, make sure we've selected it. And that's got the middle node, proceed. So that's all we need to do for those. And then we'll do the quick other velocity one. Again, change that to a node, yes. Select the middle node to where the velocity is applied, proceed. And now we need to attach these sets to the load collectors. So our velocity, we can choose our set now. We know that's velocity. Okay. The mass constraint, we choose our velocity constraint because that's where our mass will be. And then the backing plate constraint, backplate. Okay, so that's now how we can set those nodes in sets to be able to apply to the load collectors for what we need there. So next thing what we'll go through is creating the material. So this is a very, very interesting spot because we're no longer working, like we will be working in the Young's modulus section for a little bit, but the majority of this will be outside of that. So we need to change the card image from elastic when you create your material, so we'll just call it aluminium. We need to change this card image in the material from elastic to plastic Johns 0. So this is your standard M2 elastic plastic material. All the rest of them, look, as you can see, there's a hell of a lot of different types of material types here. If you have something different, like a lot of people I know work in honeycomb structures, you might even want to do some research on the M28 honeycomb because that might be of more interest to you. So definitely have a look through a few more of these other material types and see what you think would be best. Again, all these can be found on the help sections that I think I've gone through before, but if not, we'll just like that. So we'll make this an M2, but for the help, Hyperworks, help home, and you can find all these kinds of materials and help sections on there. So definitely worthwhile going through that. Okay, so with the material, you need to have your initial material properties such as your density. So for this one, we're going to call it 2.79 e to the negative 9, which is a rough standard T6 aluminium, and that will be in millimeters per kilogram. So actually we don't want that. We probably just want it 2.79 to transfer it from millimeters cubed to meters. You want your standard Young's modulus, so we'll call it 68.9, sorry, because I'm working in meters. So this is where you need to understand your units. It's very easy to muck up when you're used to working in millimeters and then working in meters. Your Poisson's ratio. Okay, so now we start to get to what we need to put in for our nonlinear part. Always recommended looking at what these sections are. So what we can actually do is on the I flag is we can change it from the classic input to a new simplified input type, which is just based around engineering stress and strain. So we can change it to that. And as you see now, it makes it a lot easier for us to understand. So we can look at the ultimate tensile stress. You would put that in. And so always build up your material decks so you understand where your material stresses and strains and the mechanical properties of them are. And definitely do reviews so you can get in the correct ones. So for our ultimate tensile stress, I think we can put in roughly, I think it's about 250 megapascals. So we'll just put in 250 for the moment. And you can have this, put in the strain. And then you got your failure at plastic strain. So you don't have to find everything for these, but the more information you put in, the better it will be. And then put in your maximum stress, say it can be 350. So yeah, definitely do some good research on the materials that you're using and the strengths and stiffnesses of them, and that's where you can find all these as they start to tell you where they are. So you can flag the strain rate computation. So here you normally just keep it on strain rate effect if you have it, as it's a pretty good default, and as you can see, default set to 1. If you really do know what you're doing with it, you might be able to have a look at the no strain rate effect. But for this, I'd recommend if you are going to have it on, keep it on 1. So we've got, and then you can look at your flag rate for smoothing. You got your cutoff frequency for smoothing. So you can see there is actually a lot of stuff to actually go through when building a nonlinear model. It's not as straightforward as a linear. And then there's full temperature components as well, but I don't think anyone here should be working in melting of temperatures, especially not for the crash structure. So you should be fine to be able to leave that. But we'll just put that in just for the moment, just so you guys get an idea of it. And then so with the other materials as well. So this is your basic M2 elastic plastic. Just some other basic material laws that you have. If you look at law 27, that is a plastic brittle material law. So I'm fairly sure that would be used like a lot for plastics. Plastic materials that are really rigid and quite brittle, they'll snap and they won't have a large plastic region. Law 28 is your honeycomb law. You've got law 14, which is becoming a composite solid. So if you are using composite structures, law 14 and then law 25 is a composite shell. So making sure you can understand the difference between that. Then if you are putting an elastic material in, law 1, it's worthy to note that law 1 in radios follows Hooke's law. So definitely making sure that you understand Hooke's law for law 1 if you are inputting an elastic material into a nonlinear run. So there is your basic overview of setting up your material. So making sure that you're consistent with your units, because as you can see then, I'm used to working in millimeters. I changed to meters and I went from 68.9 gigapascals to 68,900 megapascals. And if you have those values wrong, it can throw your entire analysis completely out. So definitely make sure you are understanding that. Okay, so now we'll create a property. Okay, so for this, there is a few different properties that you would be looking at depending on the type of elements that you're using. So the main elements that everyone here would be using is your basic tetraphores. They're probably the most recommended for any general shell structure mesh anyway. And they're also a very good default as to pose with analysis usage and computational taxing, so computational time to the closeness of results. So I really recommend trying to stick with the shell elements. If you need to use brick elements because you can't get away with them, definitely understand what you're doing with the solid meshing and understanding how to apply that correctly. But for this part, for the crash structure, we are only using shell elements because it's a mid-surfaced section, which I think we went through in the hypermesh tutorial, which would have been the second proper webinar. Shows about going through a mid-surface, and this is a section where we've used that. So definitely having a look, making sure you know what you're putting on. But for the card image, we're going to go to a P1 shell because we're using shell elements. And then what we want to do is iShell solid flag. We don't have any solids, but normally what we'll use here is a QEPH shell formulation. So we'd use the number 24 as a good default when we're using the shell elements. So we'll put that one in. And then because it's got physical hourglass stabilization, and it's the best compromise between cost and quality of your results. So flag for small shell strain formulation. I usually put some small strain on, but you don't have to. You can have, if you want to go to full geometric nonlinearities, you can. So I'm more giving the tools of what is there. Definitely do some research into each of these sections and understanding what you're turning on is always a good start. But so we can easily do full geometric nonlinearities. Now for the iShell 3, this is only for a 3-node shell element formulation. So although we are using all square elements, every now and then you can get a 3 shell in there, or it can formulate a 3 shell. So what you can do, this is only if you are using the 3 shell. So we're going to leave that blank, just use the default. We're going to use that. We're going to leave that blank because we're using hex elements. Then we move on down, and again, keep checking what they are. So you've got rotations, outer plane hourglassing, got shell membrane hourglassing. Okay, so number of layers, or this is also number of integration points. You can put anywhere between 1 to 10. However, 5 integration points is a recommended number. So what that'll give you is on the edge of each node can be an integration, and then you've got another point in the middle as well, in the center of the element. So that's the recommended. That's the recommended for these elements. Okay, so keep moving through it, and also back to the small strain formulation. Just to understand that number 2 as well can be used for large displacement and strain. So this can also be used for full geometric nonlinearities, just as number 4 can. So either one of those two should be fine, but probably recommend going for number 2 over number 4 until you understand really what this will allow your analysis to do. So we'll swap that to number 2. And then you've also got your ice strains here that you can also put in as well. So I'm going to put in yes for that, because it is flagged to compute strains for post-processing, and this is something that you do want to see the strains in. And then your element thickness, flag for, stress calculations. Definitely thickness change is taken into account. It can do, but for this, set to default should be fine. And now with the shells, so that should be all good. I think that should just be 0.03 or 0.03 should be the thickness of it. That's the damage value. Take that off. Okay, so we've got our property now as well, and we're going to then assign that to our crush structure. So we can got our property ID here, just like now. This just becomes just like OptiStruct. Applying that, and then in the actual material you can give it a thickness. So we'll give it a thickness of 0.003. So that's just 3 millimeters. Again, making sure that the thicknesses are to do with your structure. For the moving rigid, so this plate here, we'll just call that a rigid body because we don't need it to have anything else. Okay, so what we've done now is we've assigned our load collectors to our components. Our rigid body should be constrained around the flange edge, which is really good. Our plate has initial velocity, but one thing it doesn't have at the moment is we haven't put in the mass. So with this, now we need to put a mass onto this node. And one thing is, if you don't know where to find something, so if you struggle finding it in the boundary conditions or the tools, because sometimes it is very easy to forget where it's gone, I always go Control F and then you can type in what you're looking for. So mesh create masses. So now I can instantly come up to it and want to create it on a node. So for this, I want it on the rigid body node, so I'm going to remove all the other elements just so I don't select them. On the middle node there, going to give it a mass of 350. It's individual mass type, selected nodes, create. Now I've got a mass on the element, and as you can see, that's just auto to component. So now we've got a mass on that node, as well as a velocity, which is now putting it up to the 7 meters per second at 350 kilograms. Now, this is the big part of a nonlinear analysis, and that's setting up the correct connectors. So there's a large range of different connector types that you can use, but there are sort of 3 types that are the most common. And what you have is a type 7, which is called a node to surface connector. a type 11, which is an edge-to-edge connector, and a type 24, which is a node-to-surface and surface-to-surface connector. So what that means is a type 7 node-to-surface, you've got a master surface to a node, edge-to-edge, quite self-explanatory, and node-to-surface and surface-to-surface. But when selecting your master and slaves, the larger elements always become the master. That's just how you set it up. So your large elements are your master side, your master nodes, or your master surface, and the section with the smaller elements becomes your slave section. So what we're going to do is we're going to right-click and we want to create contact. So this becomes a group. So we're just going to call this plate to crash. So the type that we're going to use is a type 24. So we're going to go node to surface and surface to surface, but if wanted, I can also use a node to surface as well. So we might as well just go type 7, which is a fairly standard one. So it tells you here what you're using. In the group ID of the slave entities, you're using nodes. In the surface ID of the master entity, you're using elements. So it's asking for, well, here we can select the elements. So what we're going to do is we're going to use the elements on the actual section itself. So I'm going to turn those off. And I'm also going to turn off all the other elements. This way then I can just go and select elements, displayed, add. Now they've become the master, and as you can see the direction of the contact, which is correct because it's facing towards our crash structure. When we return out of this, we can see it. So that's so you want the contact facing the direction of the slave nodes or slave surfaces or slave elements, whichever one you're selecting. So what we're going to do is going to turn that off, and I'm going to turn this off, so then I can, just by selecting them, you can turn each component or group or set or load collector off. That way then I can just select the nodes that I want on the crash structure. So for this, sometimes when you create a connection, you might only want a small section of nodes as what's going to happen. For this, we want to have the whole face selected, because as this part moves in, it's going to crush it, and then we're going to have different connection points as it moves along. So for instance, when I first set this up, I decided that I'd only need to connect the front edge. What happened there was the analysis was wrong, because then once it pushed through that connection, there was no more contact and the velocity didn't slow down. So what we actually saw was this front going straight out the back through this plate and just continuing on, which means that the analysis was, the results of that analysis were very incorrect. So for this one, I will be setting it up so all the nodes of your crash structure are part of the slave entity. So that means that in each step that it crushes, you'll have new connection points. So I'm going to select the nodes, and you can have add by faces. We'll go by nodes. Click the nodes part and select by face. Okay, doesn't want to do it. That's all right. We can select a large portion of them anyway. So we'll just select a large portion of the nodes. And again, this will be entirely how you set up your own analysis as to where you select it, but you get the idea. So I'd be selecting the whole thing, but not the flange that's rigidized. So everything but the flange that's rigidized, I would be selecting. Add, return, then turn your collector on, and there you can see the full contact. So if we zoom right in here, each of those nodes now is a slave node, and each of these elements on the large plate are a master. So how we now distinguish this? With the connectors, you can have some large problems depending how close the connections are, how close the elements are together, whether you've already got initial penetration between the two master and slave entities. So the initial penetration is a big factor, because what it automatically does is it automatically creates a stress within the element that's not technically there. So it's a false stress, and if not monitored correctly or handled correctly, again, it can throw the results out. So this is where we start to handle these kinds of things. So what we want to look at is, first thing is removing initial penetrations. So what I will do is I'll go down to what I call inactive here. And we want to either use default set or number 6. Gap is variable with time, but initial penetration is computed. So for this result, I'll use number 6 because I want to make sure if I do have penetrations that they are computed and taken care of. So that's normally what I do as a first, just to make sure I get it right. Okay, so flag for stiffness definition. So you can have a look at a number of different ways of doing this. Look, generally defaults are pretty good for this. So if you're not sure what you're doing, I'd recommend setting it up with the defaults and until you get an understanding. So for the stiffness though, you can have that computed from both master and slave characteristics and so forth, but we'll keep it as the default. And then we can move on to heat contact. We have no heat contact. Okay. Flag gap slash element option. So what we can do is we can go to variable gap. Variable gap varies according to the characteristics of the impacted master surface. Or you can go to number 3, variable gap and gap scale correction of the computed gap. However, with this, because I normally would go number 3 for this, variable gap plus gap scale correction. You can have an airbag, but we don't have an airbag. Flag for nodes and segment deletion. We don't want to delete anything. Don't have a curvature. So then you can give it a maximum gap of the contact. For this, we're not going to give it a maximum gap, but there will be a minimum gap in a minute. You generally just go through maximum fraction. Unless you know these exact values, I tend to leave them. We don't really need to calculate these, but again, if you know the values that you're looking at for this contact, then by all means go for it. So you've got this one here, IREM gap. You don't need to set IREM gap if you have set IGAP. If you haven't set IGAP, I recommend setting IREM gap to 2. So that's only if you only set that if you haven't set the IGAP. So that's just there's no need to set them both. So normally, just for the namesake, we'll stick with IGAP at 3, and we wouldn't worry about that. Gap minimum. So this is now the minimum distance as to where the contact will start. I normally give it a very, very small gap, but also making sure that you do measure between the two entities as to where they're going to be. So when you zoom in and you measure the 2 points, so we can go function or just F4 or just F4, between 2 nodes, so we can select that node and that node, we can see our distance is sort of 40 mil or whatnot. So we don't want this to start connecting until it's well below that. So what we'll do is I'll put a minimum gap, say 1e to the -5. So now that's quite a small minimum gap, and that's the time that this contact will start. So you don't want to have that too big because you want to keep it relatively realistic, but again, it's not too much as to having a larger gap minimum because it's the way that the materials behave as well. And now, after that, you've actually set up your contact. So then we would leave the contact, jump out of that, and now you've set up your components. For this one, I would probably actually take that off rigid, and because it's been rigidized, I've taken it off being rigid and given it a part and a material. only because it does have the rigid body attached. If it didn't have the rigid body attached, I would keep it as a proper rigid part. But I'm not worrying about giving it a thickness because it doesn't matter. So what we've done now is we've set up our components, we've set up our nonlinear material, we've set up the properties of that material, we've given the material a thickness in the component, and then we've set up our load collectors with a velocity and mass. We've constrained some of them, and we've also set up our contact group. So what is to do next now? This is probably, again, one of the... we've also set up the sets to be able to apply to the load collectors. What I would recommend doing now is clicking on utility. So with this, you can always do this kind of stuff manually as well, which is, I'll just quickly show the manual way. It's in analysis, control cards, and setting up all your control cards. That is tedious, and it's also very easy to miss certain variables that you need. If you go into utility and click engine file assistant, my bad. So click engine file assistant. This helps set up a generic engine file that has all your baseline outputs to the analysis that you've set up. So one really good thing about that is it's very quick. Don't need to mess around with it too much, and it will give you a large portion of the outputs that you probably don't really need to go into the control cards. Still recommend having a look in there just to understand what you're looking at, but really this is the best way of doing it. And it's also the most stress-free way. So because with Radios, and I'll show this in a minute as well, you have two files. One that's called a starter file, which contains basically all your FE model and all your elements, all your setup, absolutely everything like that. Then you've got your engine file. What this contains is the runtime, frequency of output files, and all your variables. So there's two different file types, and that does get confusing, and this is why I recommend setting up your engine file this way. So we want to create an engine file. So we can give a termination time, so the length of time that you want it to run for. You can give it, say, 0.04 seconds. Animation output frequency. I normally recommend, for this kind of analysis, you'd probably want to have at least a good sort of 25 to 30 animation files. That would help capture all the relative information. There's no harm in going more, but I mean, any more than sort of 50, 60, it's probably overkill, because then you're just sort of getting wasted files. So you always want to calculate this to, let's say if you wanted to get 40 output files, and you calculate how many times that outputs to get 40 in the termination time. The history output frequency, I normally go a factor of 10 lower than the output frequency, than the animation output frequency. And then you can put the time history output frequency, that is that, and the nodal time step. So the nodal time step was what we had a look at earlier when you check the time step of your elements. So this is where you put all that information and making sure you select generate default output request. And then you would click OK. So I won't click OK because I'll show you an engine file now. So this here is a basic engine file that's created from that. And so what it's got here is it's got anim is animation, you've got vector contact, displacement, velocity, element strains, energies, stresses, hourglassing, nodal mass, nodal time steps, history time step, and you've got the runtime up here. So I had my one was 0.0314 seconds. And this is where all this information is. And you can also change this in Notepad++. I find it's very easy. If you want to change that to 0.04, literally hit that and then click save. And then that'll change. So I'm not going to save because I don't want to change all the variables for the run. But that's a quick way of finding some of the outputs. And then when you reopen it up, you can go into the control card section. to see, what's been selected, and you can also select some more if you'd like to get an understanding of the output. But if there's an output here that you don't want and you take it out, then it could mean that you missed some information. So I recommend just keeping all the default and only adding in more should you wish. And you can physically type them in yourselves as well if you want to do that. So that's your engine file there. And then when you run the analysis, that's the file that you use. So you need to make sure, as you can see, that you keep, and these are the two file types here. So my crash underscore 0001 dot radios, and then crash, and there will be another one, the crash underscore 40 dot rad is the starter file. So the engine file is always the smaller file, and when you generate this, there's going to be maybe only 3 files within a folder, and I always recommend each separate run you do have a different folder for it. Makes it very easy to determine which results are for which analysis. So that's a big recommendation there, because as you can see, you can generate a lot of output files, a lot of animation files. You've got your T01 and T02 files. And also with this, you can also do a restart. So one way to do a restart, and this is a big recommendation because nonlinear runs can sometimes take a lot of time. So what I would say is you'd get it set up during the day, you'd start it running just so you know it runs, and then you could stop it. This way then you can continue on with all your other work without heating it, and then you can run it overnight when you're not using your computer. And so to do a restart file, what you would do is you would open up your engine file like I have here, keep the same time, then resave it, go File, Save As, and you give it the same name like I have here. This is my restart file where I've got crash underscore 000, but I've called it 2.radios. And then when you're ready to continue running your model or your simulation, that's the file you use to run the restart. Does that make sense to everyone? So when you do a restart, you create another engine file, but keep it within the same folder so it still links to the same starter file. And that's how I would recommend to run a crash simulation like this, is running it through, overnight when you don't need to use your computer, so you can use all your computing power and it won't stop you from doing any extra work. And then to run this file, go to radios. So I just type in radios. It comes up. There we go. Oop. So this is the little screen you get for Hypercrash or radios. And then you select your input file. So which mine would be in academia, training, radios, restart and run. And then you can see your 3 starter files here, or engine files, and then you'd select whichever engine file you want to run. So if you want to run that one, and then you click run. And that's how you would set it up, set up your engine file and run it. So you use your engine file to run the simulation, not your starter. Then we can pull this out. So when we look at our results, we get something like this. And then we can click apply. And now what we can do is we can play this. Just make sure it's on transient. So to change from set modal, set linear and transient, because this is going to be moving, I'll slow it down and get something like this. So as you can see, we're seeing full non-linearities within the crash structure. The moving plate is showing the displacement, which is exactly what we want, and it's also slowing down and stopping. We can see how the major structure is starting to penetrate into the backing plate. So that isn't an ideal thing. What you'd want to do is then work out a way to optimize this so it doesn't do that. You need to optimize this structure to be able to handle the amount of kinetic energy put into it and turn it all to internal energy. So we'll do, and then we can just pause that. Now, what we want to do is we also want to look at the velocity of the plate. So we'll apply, because we want to also see how that slows down. So what we can also do is, using all these buttons down here, you can do measures, tracing, building plots, deforms, to see how the velocity changes in the plate. But we'll give it a quick play. And as you can see, that this should be slowing down. So you can see towards the end there, the large plate does get to the dark blue, which is giving us 0. So that means then, look, we're starting to see that it is stopping it completely. But how much energy that this is actually taking, we're not too sure of. So that's where our T0 files come into play. Is we can go to build plots. Oh no, not build plots. Sorry. Got to remember where it is now. My bad. Either way. So what we can do is, I'm going to open this up. Oh, damn it. Here. Oh, whoops, wrong one, sorry. So you can build your plots to obviously see what you want to look at. So this is, sorry, I will show this as well. And we can actually select the velocity. So this is how we can see, I meant to show us the velocity change in the plate. And we can select the node. Just want to select any of those nodes in the Z direction, because that's the only direction, and we can go apply. Now we can see that it's going from -7 to 0, so we are slowing down completely, which is really good. So that's one good thing we've got there. And to change these windows, you can just go back to 1, or you can select in this window bit and go back to 2. We'll go back to 1 at the moment. Just trying to find where that section is. It's not deformed. Sorry guys, I'm just having a little bit of a struggle here. So this is a look at the T0 file exported to a CSV file. And in one column, you've got your kinetic energy, which is this column here, because you can see it starts with energy. And then your internal energy is completely 0 until connection starts. This is how you can see then how the structure is performing, because as we scroll down, and this gives you all the output steps that it's giving here, and we'll scroll down, because what we want to see is all the kinetic energy get to 0, and all the internal energy, here we go, so at this point here, so I'll highlight that, this point here, all kinetic energy has turned to internal energy. So it does mean that this structure is performing correctly. In terms of the amount of displacement that it's showing, it isn't necessarily correct. So you need to then start to run your optimization on it, put in your engineering judgments to find out how to properly design your crash structure. But this is the big part here that you want to be looking at, is your kinetic energy to internal energy transfer. So I'm not too sure whether it is exactly 350 kilos at 7 meters per second, but if that's the analysis set by the FSA rules, and you've set the model up 100% correctly as to what it would be on your car, or however they want you to set it up for their test. So again, if they have a certain way of you setting it up for your test, set it up for that. Don't just go on exactly how I've set it up, because I may not have it correct with the FSA rules, or I may not have it exactly correct as to how it would be constrained on the vehicle. So it's a big thing there, making sure that is 100% correct. But this is where you want to have a look at here, is when your kinetic energy returns to fully internal energy. And after that, it's just some smaller points that, because you always have some rebound as well. So after this point, sorry, I'll just go back to it. Oh, where is it? So after this point, you will then, because it's completely stopped, and at this point the velocity is stopped, but your material will show some rebound effect. So then the energy will change again, and that's the part after that we're seeing. So yeah, hope that has helped everyone. If you want, I'm happy to finish it there, or if you'd like to stick around, and I can see if I can remember how to pull up the T01 results. That's up to absolutely everyone here, and I can work that out if you'd like. There's probably a fair few questions that have come out of this one, because there is a lot of ifs and buts, which I do apologise about. It's just more about how, the type of setup that you personally are doing as to the constraints and the model inputs that you give it. So I am more than happy to try and answer any questions that people have. So yeah, fire away if you do have them, and if you want me to stick around and try and open up that plot that T0 file in the model here, I'm more than happy to go through doing that as well. But we have sort of hit the hour, so don't want to eat into everyone else's time. But what's everyone sort of feel like doing now? Yeah, okay, so I haven't had anything come through, so what I might do is, and I might stop the recording, and if everyone likes, I can send out an email if people want to ask how they can properly view all this stuff in here. I can easily send you an email about how to do that as well. Yeah, so sorry for going a little bit over time today, guys, and girls, I should say, as well. But yeah, thanks for coming in, and hopefully this is a bit more interesting about being able to see something actually crashing or crushing. And you can definitely apply this to your own cars, even if it's something that you don't want to put into the FSAE, but you want to see how it's done. Like for instance, Ford back in 2007, I think it was, they had the first convertible with a 5-star ANCAP rating, and those results and analysis were done through the program that I just showed you here. So, very much this program is in use. It was also developed in the United States with a number of companies over there with their inputs. So yeah, this is very much in use through the automotive sector, as well as in use in defence for blast simulations. So yeah, I definitely recommend do a bit of reading up on a few different model types, because I don't even understand them all, which I can admit that there is 40 different material type sections in there. But yeah, so hopefully you've got enough of an idea to be able to try and set up a model and see how crash structure goes anyway. But look, I think I'll leave it there then. My voice is starting to go, so I apologise for that as well. But yeah, have a good day, guys, and I will get out all the rest of the stuff for the next one. So next week, hopefully we'll have a really good one. I've got Ricardo coming in, hopefully for 5 to 10 minutes, have a chat to everyone about CFD. So it'd be really cool to have heaps of people there for him. I'm sure everyone through the FSA knows him, or at one time or another has had him critique and sometimes obliterate everyone's designs. But yeah, he's a pretty good guy, and he's agreed to come in for 5 to 10 minutes to talk to everyone about the CFD and why you should implement that as well. So next week we'll be doing the aerodynamics side of things. But thank you very much, and enjoy the rest of your day.